We're gonna get started. First off, I hope everyone had a great Thanksgiving break. You know, good to just kind of like get away from all this stuff and relax. Um, we just got a little bit left. A little bit longer to push through, and then we'll be done. This is your last lesson that you have to learn. After this, it's just gonna be a review for the final. So let's just try and finish off strong. So with that, right into the lesson. All right, so just going way back to back for your first midterm, we talked about correlation. So it's just the relationship between two quantitative variables. So when you're looking at a population, you're going to use rho. It's got that kind of symbol that looks like a p. And then when you're using for the sample, you're just going to use r. You can find this with Minitab, and then if you're looking at the value of R in comparison to its like strength, regardless of whether it's positive or negative, these numbers still have like the same strength. So from 0 to 0.2, it's very weak. From 0.2 to 0.4, it's weak. From 0.4 to 0.6, it's moderate. From 0.6 to 0.8, it's strong. And from 0.8 to 1, it's very strong. And you can't go above 1. So we're using this for hypothesis testing. It's the same 5-step procedure. You're gonna check your assumptions. So your assumptions for this are that both variables have to be quantitative and that the relationship between x and y must be linear. For calculating your test statistic, you're just gonna use Minitab for this. For your p-value, you're gonna get this from whatever software you use, so Minitab, but what's gonna happen is it's gonna give you a p-value for a two-tailed test. So if you need something where it's a one-tailed test, if it's saying it's less than or greater than rather than just if it's not equal to, then all you have to do is take that p-value that you got and divide it by 2. And then from that, you're going to make your decision and then state your real-world conclusion. So for a simple linear regression, again, we kind of already talked about this before. You basically use it for its one-way explanatory variables and a straight line. That's how you use it. And with it, you can basically like predict a value if you know the other, like if you know the slope and everything. That's what it's used for. As we said before, it highly is similar to going back to like your basic algebra of y equals mx plus b. So your y hat there is the predicted value of y for any given value of x. Your b sub o is the y-intercept, and your b sub 1 is your slope. So your assumptions when you're using a simple linear regression is that, first off, it's going to look like a line. If it doesn't, then you can't really use it. Independence of errors. Basically what that's saying is that there's no relationship with the errors. Like you can't see a relationship on the graph. The correlation between these errors is basically 0. Normality of errors, basically what it's saying is everything is normally approximated. And equal variance, that's basically saying that the errors have no pattern. So that's the assumptions that you need to check to be able to use simple linear regression. All right, so confidence interval for a slope. You calculate using this nice little equation of b sub 1 plus or minus t times standard error of b sub 1. So b1 is just your sample slope for this. The t is the value from the t distribution when degrees of freedom equals n minus 2. And your standard error is just standard error of the sample slope. And confidence coefficient of determination, it's r squared. So it's the amount of variation in the response variable that can be explained by the explanatory variable. So basically you just take whatever your r is and you square it, and that's your coefficient of determination. And lastly, just some things to always be aware of when you're doing this stuff. Outliers, they're dangerous little things that they'll affect the graph. And the most important thing is they will change, the correlation value. So you always have to be conscious of that. And then one other thing is just, God, I can't pronounce that word. Basically what it's trying to say is that you can't use the data that you found in one thing for trying to find something else. So for instance, if you have the data, if you have like an equation of data for the average temperature in a set number of cities above a certain latitude. So let's say if you're going from like Miami to New York, then you can't use that data for a city that is not thanks, Matt. Extrapolation. Thank you. I needed the fanatical spelling. Anyway, so if you are trying to find a city who's not in that like latitudinal range, let's say it's like Mexico City, or say it's something way up in Alaska, then you can't use the set of data that you already have because it would most likely give you an incorrect value. So with that, we're already into review number 1. So this is basically just asking, why would you use, what can't you do with our regression equation? So I'll give you guys a little bit of time to answer this, and we'll go over it. All right, yeah. So we're going to go over it. So the answer is C. So the value for this is that you can't really determine whether it's going to be linear or nonlinear just by the equation. You're going to have to like graph it out to see, versus all the other points. If you just plug stuff into the equation, you should be able to determine what it is. Like B, that's exactly why you'd use the regression equation, is just to predict the value of Y. If you're estimating whether it's positive or negative, again, you just plug in some values and you'll figure it out. And estimating the slope, if you have all the other data, you can find the slope. So the only thing that you can't do is just guess whether it's linear or nonlinear. All right. So into number 2, research question: can you use height to predict shoe size in elementary school children? So all this is asking it for is what's the explanatory and what's the response variable. So I'll give you guys a little bit of time to just type that in the chat. All right, got it. The explanatory is the height, and the response variable is the shoe size. Good job. All right, so basically just going with that, we're going to be using the regression equation, which is right there, to basically calculate the predicted shoe size of someone who is 67 inches tall. So I'll just give you guys a little bit of time to go through this. Yeah, good job. Just simple plug and chug. Just take the 67, plug it in for your x, and then you end up getting this, which is just round to 9.15. All right. So this is asking about the coefficient of determination. So it's giving you an R value, and it's basically asking what portion of variation y can be explained by variation x. So I'll just give you guys a little bit of time to go over this. Shooting from the hip, eh? All right. So we'll just quickly go over this. It's actually A, because basically we're just gonna, sorry, just gonna shoot back a little bit. So coefficient of determination, it's literally just R squared. So you take whatever R value they give you and you just square it. So I just wrote it out. You're just doing 0.8 times 0.8. They end up getting 0.64, a positive, and they just switch over into percent by just moving the decimal place over 2 spots, and that's how you get 64%. So what that's saying is that 64% of the variation in y is explained from a variation in x. And with that, yeah, we're done. So thanks for coming out, guys. Gonna be having my next session on at Sunday, same time. Have a good one. If you have any questions, let me know. I'll be sure to answer them.